Okay, so once again, good morning, everybody. So let's get started. Um, Let me share my screen. Can you see my screen? Like transformer?
Yes.
Yes.
Okay, thank you. So today we will start the new chapter, transformer, and we'll be looking what are the functions of transformer, what is it, uh, its magnetic circuit, what is the relationship between input and output, voltage, current, power, and one new concept, impedance transfer through a transformer, and then problems. Uh, so first of all, you know that what is the transformer? So if you see, like I have written down the definition, transformer is a static device that transfers electrical energy from one circuit to another through inductively coupled conductors. That means the transformer coils. And it is the most efficient electrical machine. So, as you know, in the first class, I was explaining you uh, the energy conversion means conversion of energy from one form to other. There were generators and motors, but in case of generator and motor, there were rotating parts, there are moving parts. I mean, there are coils, there are magnets, but either magnet or the coil will be rotating. So once there is any rotating body or rotational body, then there will be some friction loss, windage loss, some other losses. That's why in case of motor or generator, whatever, you will not see the efficiency never ever more than 80% or hardly 85%. In most cases below that level. But in case of transformer, efficiency is always high, at least 95% or much more higher. I mean, close to 100%, always. Why? Because you see that definition, this transfer electrical energy from one circuit to another circuit. This means it is electrical to electrical conversion. There is no mechanical component here. This means there is no rotating parts. So because there is no rotating parts, there is no friction loss, windage loss, bearing loss, stray loss, or other type of loss. There are little resistance inside those coils. There are little I mean the very little loss, but that is almost negligible. That's why, I mean, not today, maybe next class, when we'll be solving some problem about transformer efficiency, always you will see efficiency is at least 95%, pretty close, 99%, pretty close to 100%. That's why it is called the most efficient electrical piece of equipment. So therefore, you might be asked this question, for example, in job interview or in FE exam. So what is the most efficient piece of electrical device or component? That's the transformer. And I myself always treat this component as the heart of the power network. Like the way you have your heart, I have my heart in my body. Similarly, transformer is the heart of the power network. Without that, the system will not run. I mean, we will be under dark. So we are gradually coming that point. So then, what are the primary functions? To transmit AC power to long distance. So because if you develop voltage, for example, at the range of 11,000 volt, and at your home the requirement is 120 volt for a single phase system, but there will be drop. So that's why you have to put transformer, because transformer can step up or step down the voltage, current, or the power level. So this means the distance between your home and then the power plant could be 100 miles, more than 100 miles, 500 miles. It's long distance. So therefore, how you will transmit power? because there will be voltage drop. There are power losses. That's why to transmit AC power over long distances, transformer are used. So that is the number of function. So therefore, so you all know, first of all, you can transmit the DC power over long distances. You cannot, because you cannot increase or decrease the DC voltage. I mean, although there are some power electronics mains, that is different thing. But we're talking about these conventional power lines. You can't transmit DC power because it will produce constant flux, constant magnetic field. That's why DC power transmission is not possible. And that is the motivation to invent, to explore the AC. And transformer is the AC device, keep in mind, not the DC device. So therefore, in addition to transmitting AC power to long distances, what else it does? It step up or step down voltage. Or whatever level you need, you just need to design the coil number of turns accordingly. Then it can increase or decrease voltage. Similarly, it can increase or decrease the current. And also, it provides isolation between two circuits. I mean, soon I will be showing picture because there will not be any direct connection, electrical connection between two sets of coil. They are just magnetically linked, not electrically. So this means you are able to provide isolation. In some applications, you need to isolate the circuit. That is the meaning. So these are the primary functions of the transformer. And you will find, if you read the literature, I mean, not just the book that we are following, if you read literature or if you read any article about transformer, you will see different types of transformer. So these four types are main, and they call the power transformer because these are very high rated in the range of megavolt ampere, typically used in the entire power network. So first one is called primary or step-up transformer. Then second one is called grid or substation transformer. Then third one is called secondary or step-down. And then the fourth one is called the distribution transformer. So therefore, just in a minute, I like to show you which transformer is what. Uh, just a moment. Okay, so everybody, if you see, uh, so this is the main power plant. So right after that, you need one transformer. So this is called the step-up transformer, primary or step-up transformer, which is very close to the main generator, main power plant. So this is the step-up. So step-up transformer, step-up or primary, this transformer. Okay, right after that, with a little distance, that distance could be only like even less than a mile, there is another transformer in real practice. This is called grid or substation transformer. This transformer. This is the grid or substation transformer. This one. Okay, then after that, the transmission line is going on. I mean, before I have explained you this thing, this diagram briefly, this is the transmission line. At the end of the transmission line, there is one transformer which steps down voltage, and as I told you before, that converts into 33 kV. This transformer is called the secondary or step down transformer. So this transformer is secondary or step down transformer. So after that, there is one more level. So from here, go down. I mean, for use of the people. So therefore, uh, this one is called distribution transformer. This means with the distribution transformer, customers are mainly connected. So therefore, these are the 4 types of transformer. All are called the power transformer because they all are at the high power level. I mean, consumer is much more at the bottom. There is another small transformer, which converts 11 kV to which voltage you need, like 120 volt for single phase system. So everybody keep in mind. So for example, you are reading a literature or you are listening to someone's lecture about transformer, and they are using this type of term, secondary transformer, distribution, substation, or primary, then you will concentrate at that portion of the network. So therefore, once again, step up or primary transformer, which is very close to the generator. Then after a little distance, it is called grid or substation transformer. After that, this is long line. There is nothing here except the cables, high voltage cable. Then you need to step down. Then that is the secondary or step down transformer. After that, people need to use the power. Gradually, it will be step down up to the required level. So those transformers are called distribution transformer. So everybody, could you follow me?
Yeah, I have a question.
Sure.
So would like the green box transformers like outside your house, would that be a distribution transformer? And then the ones like on the pole before the wires go into the ground, would that be a secondary or step down transformer?
Yes, you could interpret in that way. But the transformers which are nearby your home, for example, those are mostly the distribution transformer level. So therefore, this secondary or step down, this one, for example, this is actually the MLGW location. Therefore, they have on big transformer. You see the here, the primary side of this transformer, this is very high voltage. For example, 345K or even the much more, this side. Only this side is 33 kV. Therefore, this is the MLGW location. Therefore, the transformer that you mentioned, those are much more downside, like your home or nearby your home. Those are the under the distribution circuit. So that's why accordingly those are called the distribution transformer. But this one kind of, you can say, this one in a substation or the main station. This is the main MLGW location. So,
Okay, so it could go through 2 distribution transformers before it actually gets to your house, or more than.
in real practice, I mean, I am just showing in that online, it is called the feeder. Some line is going here, some line is going here, some line is going here. For example, if this is MLGW, one feeder is going to Bartlett, one feeder is going to Cordova, one is Collierville, one is Germantown. That is
Yeah,
the meaning. Got it? Yeah.
but it looks like it hits a transformer on the pole, and then it also hits the transformer that's in the green box.
Exactly. Yes.
Okay.
Yeah.
Thank you.
Yes. So here, like very briefly, I'm trying to make you understand that where those transformers are located here, briefly. But like in real practice, you see from here, from MLGW center to, I mean, greater Memphis area, as I mentioned, you like Collierville, Memphis, Cordova, Germantown, Bartlett, there are many, I mean, small size transformer. Those all you can call the distribution transformer. Okay, so then now again moving back. Okay, so therefore at least you understood what's the transformer, what are the primary functions, and what are the main type. Yeah. Okay, now, and then the one important thing, you see, specifically I am using the term power transformer. So by the word power means high power. So therefore, for example, in laboratory, you might use transformer, or for your own project, you are using some small transformer. Even, In electronic circuit, there could be a small size of transformer. Those are not the power transformer. You will be using the simply term the transformer. So here the specific keyword like power to indicate the high power level, as I showed you the locations where the voltage is high. That is the meaning. Okay, moving forward. So everybody see the working principle of transformer, and then specifically I have used the term ideal transformer. Ideal transformer means we are assuming there is no loss. I mean, in real practice, there is some resistive loss because inside the coils, there will be, even though small, there will be some resistance value. But when I am using the term ideal, I am assuming those are pure coil, there is no resistance. That is the meaning of the ideal transformer. Everybody keep in mind. So what is the working principle? So you see, this is a core body. This is a magnetic material, this rectangular body or the square body. And you see on the left side, the red colored coil. This is one set of coil. On the right side, there is that green colored coil. So as you can see, those two sets of coil clearly not electrically connected. They are isolated, but they are mounted on the same magnetic material. That is the thing. So therefore, what is happening? You see, I have written primary winding. So this is primary voltage, primary current. So you applied some AC voltage here. You want to increase or decrease, whatever it is, increase or decrease. It depends on the application. So you applied some AC voltage on the primary. You will be getting voltage on the secondary. So therefore, how? Once you apply the voltage, this means the current is flowing. This current is IP. And then can you see that green colored thing? Magnetic flux. So because you applied the voltage, consequently there is another induced voltage on these coils according to this one, Faraday's law of electromagnetic induction. Voltage will build up. Consequently, there will be current, and that current will cause flux, which is that magnetic flux. And the property or the characteristics of the flux, because this is a magnetic material, that flux will start flowing through the magnetic material. So you see, it is going, then it is coming. So this means because I already placed the coils, these blue colored coils on this side, and the flux is coming, and that flux is alternating in nature. That flux is not constant flux. Everybody keep in mind, this flux is sinusoidal flux, time varying flux, because it is being developed from the voltage or current that has been applied here. So because this is alternating or time varying, consequently, this flux is also time varying. And that is the reason it can develop voltage on the secondary side. Because you have one set of coil, and then your flux is coming, and that flux is time varying. It is changing on time. Now, everybody see, this is the difference. Now, if you apply DC voltage, everybody look seriously. If you apply DC voltage, then same thing will happen. There will be flux, this flux will go, but that flux will be constant flux. It is not time varying flux. This means once this flux will come here, it will interact with this coil. This coil is static, it is just placed, it is not rotating. That DC flux is also constant. That is not time varying. Therefore, no voltage will build up on the secondary. That is the reason never ever DC works in case of transformer. So what it will do? It will just cause some sort of heating because you know that flux will go and it is constant flux. It is not producing voltage. Just this magnetic material may be saturated, may be overheated, may be damaged, and also these coils might be a little bit heated up and over the time might be damaged. So that's why it is recommended not to apply the DC on the transformer. Okay, so therefore now because we are discussing transformer, we applied the AC voltage which is time varying. Consequently, it developed or it produced time varying flux. Therefore, voltage will build up on the secondary side. That is the Vs. And then if you connect a load here at the secondary side, then the current will flow. Now, as you can see, so the red color, the primary side coil, it has a particular number of turns. I have written primary winding Np turns. Uh, yes, Np turns. The secondary turns, this means these blue colored coils, they call the secondary winding, they have Ns turns. So turns means, you see, this is on turn. So therefore first it is like coming and then on twisting, this is on turn. And then again you are twisting number 2, number 3. Each time you are twisting it, it is making on turn, on turn. In that way, like in real big transformer, there could be several thousand turns. Here just example. The same thing on the secondary side. Now, everybody see the from the physics you already know, or even in the circuit analysis 2 course, you all studied magnetically coupled circuits, exactly the same thing. What I have written, the voltage induced across the secondary coil may be calculated from Faraday's law of induction. So which states Vs, this means secondary voltage, equals to Ns, secondary number of turns, d phi by dt. You see, this is the thing that I was emphasizing, that phi, this means this flux, which is varying with time. That is the time varying component. That's why d phi by dt. So this means, sorry, okay. So here just everybody one second. So for a moment. Um, Actually, what happens, I mean, I'm briefly drawing. This is the primary, secondary. So it has the number of turns. Sorry, this is NP, and this side is NS, secondary. And then the voltage build up here on the secondary side, which is Vs. So in this side, the voltage is Vp. Okay, so therefore concentrate here. So we were discussing how much voltage is developed on the secondary. So according to Faraday's law of electromagnetic induction, Vs will be proportionate to d phi by dt. This is Faraday's law of electromagnetic induction. This means if you have a coil and if you see that there is flux, so this is the flux, and that flux is changing. This means this is time varying. Then, according to Faraday's law, the voltage will build up on the coil, and that will be proportionate to rate of change of flux. Now, because this is proportionality sign, we want to make it equal. So that's why the next line is Vs. I want to omit this sign. I put equal. So you all know you need a constant. That constant is that number of turns multiplied by d phi by dt. So everybody, could you understand this one? So initially voltage is proportionate to d phi by dt. At what rate the flux is changing, alternating flux. And then in the next line where we want to use the equal sign, so you need a factor, k factor. In this case, that constant factor, k factor is ns, number of turns. That is the meaning. This means you can see clearly with the increase of the number of turns here, your voltage will increase. If you decrease, then voltage will decrease. That is the meaning of this. Okay, now again I am going back there. So therefore everybody see this equation that I just explained. This side Vs Ns d phi by dt. And where Vh is the instantaneous voltage, Ns is the number of turns in the secondary coil, and phi is the magnetic flux through one turn of the coil. So similarly, on the primary side, this side, when you are applying the voltage, you could make the similar relationship, Vp Np d phi by dt, because this is the common flux. This is linking both the primary and the secondary. This is a common flux. Now, everybody see, if you, this is one equation, this is other equation. If you divide this equation by this equation, so what we will be getting? Vs over Vp. Look here, Vs over Vp. And right side, d phi by dt, d phi by cancel, Ns over Np. I am dividing this equation by this. So therefore, I got on relationship. So everybody see how it is related with the number of turns. And then you see the definition, Np over Ns is called the turn ratio and is the primary functional characteristics of any transformer. It is the turn ratio. It is the number of turns on primary and secondary coil that will govern the functionality of the transformer. That is the meaning. Now, moving forward, if I go to the next slide, so everybody see, I have tried to draw that equivalent circuit. So everybody see, I am applying alternating voltage, current is flowing, there is a coil, it induced voltage according to Faraday's law of electromagnetic induction, which is EP. But because we are discussing the ideal transformer, we are neglecting the little resistance inside these coils. Therefore, this Vp and EP is the same. That we are making the assumption. Number of turns Np, this side number of turns Ns. The secondary voltage is Es. We have assumed there is a load and the voltage here is Vs and current flowing is Is. Now, you see, I have written down on relationship that relates primary, secondary side voltage, current, and the number of turns. So here you see Vp over Vs, Vp over Vs is Np over Ns. Just first look the voltage and the turn ratio. But see the current, Is over Ip equals to Np over Ns. It is opposite. It is not like Ip over Is. Then it would be pretty easy to remember. You see Vp over Vs, Np over Ns. So Vp, Np, Vs, Ns. It is easy to remember. But once it is current, it is like opposite. Ip is in the denominator. Is is in the numerator. Therefore, why this thing happened? Therefore, see the explanations that I have provided below. Everybody read this one. Ideally, the transformer is perfectly efficient. All the incoming energy is transformed from the primary circuit to the magnetic field and into the secondary circuit. If this condition is met, then the incoming electric power must equal the outgoing power. So this means that, so you all know the law of conservation of energy. I mean, energy can neither be created nor destroyed. It can just be converted from one form to other form. So this means on the primary side, I have what is the power? Vp multiplied by Ip. That is the incoming power. And then it should equate the outgoing power, Vs and Is. So if I write this thing, then what you are getting? You see Vs over Vp, then you are getting Ip over Is. But already I defined that Vp over Vs is Np over Ns. That's why when you are making the relationship, it is Vs here, it is Ns here, but then for Ip, it is here. Just to maintain the law of conservation of energy. Therefore, everybody, you will be remembering this equation you can note down. I mean, soon we will be solving numerical problems today. We will utilize these equations. So just keep in mind that NP over NS, that is called the turn ratio, and that is making the relationship between primary and secondary voltage and primary and secondary current. So is everybody fine so far?
Yeah.
Okay, great. Now we want to move forward further. You see what I have written here? The RMS value of the induced voltage. So this means we said that once we apply the voltage, it will induce voltage here, or in the secondary circuit, voltage will be induced. What is the amount? What is the RMS value of that? So this is the amount. E, this is the RMS amount, 4.44 F N phi m. Therefore, this F is the frequency, applied frequency, because you are applying the sinusoidal voltage. What was the frequency here? That is important. Frequency. N was the number of turns, and phi was the magnitude of the flux. And everybody see, this equation is equally applied to both sides, either primary side, secondary side. The same equations is true or valid. Now here I am showing you how I got this thing, this number 4.44. So everybody see, we discussed this thing, Faraday's law of electromagnetic induction, which you can apply to both sides, primary side coil, secondary side coil. So assume that the instantaneous value of voltage is N divided by dt, where N is the number of turns. And then I am assuming this phi, as I was telling you, that this magnetic flux, this is sinusoidal. So that's why I am assuming that phi is phi m sine of omega t, because that is varying with respect to time. So this phi m is the magnitude. Therefore, see the next line. Oh, sorry, first you substitute this on here. Plug in this phi value in this equation and then make d by dt. So after substituting phi here, if you make d by dt, you will be getting this line. Everybody see? E, this n is here, and then this phi m is this phi m. And but because it is sine omega t, so you will get omega cosine of omega t. So I got this expression. And then what is omega? Omega is 2 pi f. 2 pi f. This is angular frequency. So now this is my final expression. So everybody see, what is this one? This is also a sinusoidal function. The whole thing, this one, 2 phi f and phi m, this portion is the magnitude, like E equal to Em cosine of omega t. So this whole portion is my magnitude or amplitude. But this is, you see, small e is the instantaneous value, instantaneous induced voltage. What is the RMS value of that? When I am using the RMS value, that time I am using the capital A. And this means this amount, this magnitude over root 2. I am dividing by root 2. So you remember the single phase AC circuit? At that time we discussed, in case of a sinusoidal voltage or current, the RMS value is magnitude divided by root 2. That is the thing exactly I am doing. Therefore, if you have a calculator, you do 2 pi divided by root 2. That will give you this 4.44, and then Fn and the phi n. So this means from now on, you will be using this equation to calculate primary side or secondary side induced or the developed voltage, which is the RMS value. This means you need to know frequency, number of turns, and magnitude of flux. And to solve the numerical problem, also you need to know this relationship that relates the flux and the inductance and the current and number of turns. So everybody will keep this in mind. L equal to N phi over I. So excuse me, Does anybody say anything? Okay, then now moving forward. So everybody please note down this equation in your note and the last equation, the first equation and the last equation. That will help you solve the numerical problem. Now see, I have set up one numerical problem here. Everybody read the statement. Determine the primary induced voltage of a 60 Hz transformer having primary number of turns of 100. Assume the mutual flux waveform can be expressed as phi 10 sine of omega t milliweber. Also, if the primary coil has an inductance of 2 Henry, then calculate its magnetizing current. So here it says the mutual flux waveform. Mutual flux means actually this flux. It is called the mutual or the common because the same flux is linking both the primary and secondary coils. Therefore, sometimes instead of just magnetic flux, it is called the mutual flux or the common flux. That's why that is it said here. Mutual flux waveform can be expressed by this one. Now you see the main question is the very first line. Determine the primary induced voltage. So you see that is my equation that we just looked in the previous slide. RMS value, this one. So frequency of 60 Hertz. It is given in the first line, 60 Hertz. Number of turns clearly mentioned 100. Now I need phi m. You see, what is that phi m? We discussed that phi m is the magnitude. But in the statement, you see the beginning of the third line, waveform can be expressed phi equal to 10 sine of omega t. This is given in terms of time varying quantity, instantaneous quantity. So this means 10 is your phi m because this is the magnitude for this waveform, but that is in milliweber. So that's why you see for phi m I have written down 10 and I converted into Weber by multiplying with 10 to the power minus 3. So the unit is volt. So ultimately I am getting 266.4 volt. Everybody, could you follow me?
Yeah, I think so.
Yeah.
Yeah, thank you. Yeah. And then there are the second part. If the primary coil has an inductance of 2 Henry, then calculate its magnetizing current. So this means this magnetizing current, in fact, that current I, because that is actually magnetizing. If you see this one, the current initially that is flowing, that is actually exciting or magnetizing this coil. Or in other words, the core material is actually excited or magnetized by the application of the current. So that's why sometimes it is called magnetizing current. I mean that primary current. That is the meaning. So that's why it says calculate the magnetizing current. So we learned this equation in the previous slide. So Ln phi m over I. So I is this one. I am just plugging again those numbers. So L value, it is given 2 Henry. I put that 2 and number of turns and number of phi. So I need 0.5 ampere current. So this is the amount of magnetizing current. Okay, I mean, this was easy problem. Just I wanted to show you the application of this equation and this equation, how we can utilize in the problem. And then again, by tomorrow you will be submitting the first set of homework. Once you submit, immediately, like my homework is ready, the second set I will upload and then you will start. At that time, you all need to apply these equations and then much more. Now everybody see another problem. Gradually we will go little bit complicated. After this one, there will be another complicated problem I will be discussing today. Everybody see, this is another example. Assume that 60 Hertz 250 kVA 2400/244 distribution transformer. Everybody see, transformer rating is always expressed in that format, this/this. Therefore, you will assume that The first one is the primary voltage. This one is the secondary voltage. It might happen that it is the opposite. 240 is written here, 2400 is here. That is also fine. In that case, 240 will be primary, 2400 will be secondary. Therefore, currently, as it is 2400, that is primary voltage, this is secondary. This means this is the example of step down transformer. So everybody, could you follow me what I am telling?
Yes, yes.
Yes. By default, you will assume that, okay, this is primary, this is secondary. Yes. And then this is the rating of the transformer, 250 kVA. So the one important thing is that you will remember, keep in mind always, transformer is always rated in terms of volt ampere. I mean, in this case, it is kVA or it might be MVA. It is never ever rated in terms of kilowatt or megawatt. So therefore, you will get the answer why. So in this class, we will be discussing, hopefully next class or other class. But at this point, everybody keep in mind that transformer is always expressed in terms of MVA or kVA. This means volt ampere, not in watt. So this means there is a reason. But if you, when you will be solving problem for generator motor, always the power will be expressed in terms of kilowatt or megawatt, or sometimes in terms of horsepower. But transformer is different. It is always expressed in volt ampere. Keep in mind. And then you will be able to answer that the reason why it is expressed in kVA. Just wait, I mean, one or two more classes. Okay, so then what is the question based on this? These three informations are given: frequency, its power rating, and the primary secondary voltage. What's the turn ratio? What's the value of the load current, that is I2, if a load impedance connected to the secondary, that is the low voltage side terminals, makes the transformer fully loaded? Question number C, what is the primary side, that is the high voltage side current? Question number D, the value of the load impedance referred to the primary side. This part is the difficult part, that in the circuit analysis 2 course, I mean, we did not discuss these things. I mean, this is the new part of the transformer, and from now on, all will be the new thing that we have not covered in the magnetically coupled circuit, circuit analysis 2 course. Okay, and then just here, I mean, ahead of time, I have written down two formulas, two equations to answer to question number D. The value of the load impedance referred to the primary side. This means because load is connected on the secondary side, you are able to find out the secondary current, and you are able to find out the load connected secondary side. But here the question is, value of that load impedance referred to the primary side. Even it could be, for example, there is impedance on the primary side. What is the value referred to the load side? So that's why we have to use this equation. Load impedance referred to the primary side. I am discussing the answer question number D. I mean, we will be solving the full problem soon. So we will be using this equation, GL prime A square into GL, where GL is the load impedance. GL prime is the answer to this question number D. And what is that A squared? A squared is the turn ratio squared, that Vp over Vs or Np over Ns. Or similarly, primary side impedance referred to the secondary side is this. GL prime is GL over G1 over A square. So I am showing you what is that. Soon I am coming that point. So first of all, so everybody see this one. And let's, I have taken this example from the book that we are following mainly. So example 4.2. So therefore here, see that solution. Let me zoom in. Okay. Can you see clearly now? The first question was, what was the turn ratio? So the turn ratio of the transformer You see the symbol A. So symbol A is used, a small letter A is used to indicate the turn ratio. This is a commonly wide and commonly accepted symbol. So which is N1 over N2, V1 over V2. Just symbol on and to is used to refer or to indicate the primary side, secondary side. So although we learned with the symbol P and S, primary, secondary, but 1, 2 means 1 means number on side, which is the primary side. 2 means the right side, secondary side. Therefore, everybody see 2400 over 240, V1 over V2. So you see, this was the rating of the transformer. So this means this one is V1, this one is V2. So that's why I did V1 over V2 and you got the 10. That is the turn ratio. The second question was, what was the value of the load current? You see the value of load current, that is I2. That was the question number B. So everybody see, since the transformer is an ideal transformer, it has no losses. So how you will get that one? If you see the statement, you have only three quantities, three ratings given. You know V1, V2, you know the kVA rating, you know frequency. There is no information on the primary current or secondary current, and that's the question that you have to find out. So therefore, everybody see this one. You learn this thing. You have to keep in mind this equation. What we learned? VPIP equal to VSIS to maintain the law of conservation of energy. So exactly here you see, uh, look this equation. So this means S is V1 multiplied by ion, primary side voltage multiplied by primary side current equal to secondary side voltage multiplied by secondary side current. This is that equation. So this means that is the, you see, there is only one rating. You see, pretty interesting. There is primary voltage, secondary voltage. There is primary current, secondary current that will be calculating, but kVA rating is only one. That is the thing. And that is the reason that it is maintaining the balance between the left side and right side, primary side and right side, to maintain the law of conservation of energy. kVA rating will not change. Only you are changing, you are increasing or decreasing the voltage and current. By increasing or decreasing voltage or current, you are maintaining the balance. That's why you see there is only one reading. It is not like primary side on kVA, secondary side is different kVA. In this case, you see the voltage is reduced 10 times, but then soon you will be showing current is increased 10 times. The same thing on the primary side, this is that this voltage is 10 times higher than this one, but you will notice the primary current is 10 times lower than the secondary side. In that way, that is maintaining the balance. So now see everybody, this is my equation. I want to calculate the secondary current or load current. What is my S? So I am using this part. S equals to V2 I2. So I2 is S over V2. 250 kVA was the reading. It was converted into volt ampere and V2 was 240 volt. I got this current, you see, 1041.67 ampere. Now what will be the primary current, corresponding primary current? Now use the first part or use this relationship. Ion over I2 is on over A, or I2 over ion is A with the help of turn ratio. So we are using this equation because we already calculated the A. But still you can use this equation. S equal to V1 multiplied by ion. Ion is S over V1. That will also work. You will get the same result. So here we got ion is this or C that I was taking S over V1, this one. Now look this number and this number. This one is 10 times larger than this one. But you compare the voltage, this voltage and this voltage, secondary side voltage are 10 times smaller than the primary voltage. So in that way, they are maintaining the balance. And then the other question was, Question number D, the value of the load impedance at the secondary side. So first of all, load impedance is ZL V2 over I2 because you will connect the load on the secondary side. So you got this one. I2 we already calculated here, this number. So you are getting 0.230. But the actual question was, what is the value with respect to the primary side? What was the load impedance value or referred to the primary side? So that we are using this equation, GL prime A square GL. I am showing you how I got that on, how I derived. Soon I am showing you. So everybody see, I am using that equation. So here you noticed it is A square, but what is A? A is N1 over N2. A is the turn ratio, N1 over N2. So that's why here N1 over N2 is squared multiplied by what you got here. So you see it increased and 23.04. This means meaning of this on the secondary side or load side impedance when considering from the primary side, it has this value. That is the meaning. So now I want to show you that how I got this one, why I am multiplying by the turn ratio squared. So therefore, see my derivation. Everybody see this one? This is the primary side. This is the secondary side. I have primary side voltage V1. I have secondary side voltage V2. I have connected a load which is ZL. Primary current, secondary current, primary side number of turns, secondary side number of turns. So you see, I have written down what is the value of the load impedance ZL, V2 over I2, right? So the question is, if we transfer this impedance in this side, everybody say, it is located here. But if you think, if you consider this impedance is located on the primary side, what should be its value? Now the question is, why do you need this one? Or when to consider this situation? So soon I will be solving another big problem. That time you will understand why I need to think that this could be located here. Or then there can be one impedance here. You might need to think or consider that that is located here, just for the circuit calculation. Soon in another problem we are coming. So everybody see, now everybody look this diagram, what I did, it was located here GL, but I have transferred it on the primary side. That's why I have given the name GL prime. So at least you can understand it is not that GL value will be the same on this side, right? Because it is related with the turn ratio. That's why it will have a new name, which is GL prime. And then what is in the secondary side? Now here I don't have anything, so just I made sorted. So this is my new circuit. I have transferred this on here. Now that is the question, what should be the value of that? So everybody see, because now I have placed it in the primary side, so I can say at least that GL prime is V1 over I1. What was my initial voltage and current? It is related to that. Now everybody see, actually that GL, this one was located here. I transferred it here. Definitely you can understand that there is relationship between this voltage and this voltage, this current, and their turn ratio. Definitely there is relationship. It is not like straightforward, you will be placing it here. So that's why GL prime is V1 over I1. And how I can relate to the secondary voltage? What is V1? A V2. See the definition that we are learning today. A equal to V1 over V2. So therefore I am replacing V1, substituting V1 by A V2. I did that. Again in the denominator I have ion. I want to make a relate with I2. See the definition of A. A is I2 over ion. A is I2 over ion. So therefore, what is ion? Then I2 over A. Now see here what is happening. See the calculation. This A would go in the numerator. So it will be A squared. So that's why I have written GL prime is this A squared V2 over I2. What is V2 over I2? That initially we defined V2 over I2 is ZL, the load impedance. Substitute that value. So now I got GL prime is A square into GL. And then what is that A? Sometimes A is expressed N1 over N2, the primary term and secondary term ratio. So you can say A is N1 over N2 squared. That's why I am using that equation to solve that last part, this one. Everybody, could you follow me? What I explained?
Yeah, makes sense.
Yes. So therefore, I mean, this is I derived, but in the homework or in exam or solving problem, you don't need to derive. You will just remember this one. I'm just showing you that how I got that on that I showed you. So you will be directly using GL prime is A square GL. From today, I mean, throughout your life, you will remember this equation. I mean, soon I will be discussing another problem. Frequently, we need to use this expression, A square into GL, and you all need to remember these things. You see, A. This relates voltage, V1, V2. This is the difficult to remember, I2 over ion. Keep in mind, it is not ion over I2. But this is again easy to remember, N1 over N2, V1 over V2, but only for current, I2 over ion. So today we will be extensively using all these equations and this equation in a problem. Okay, so now moving forward, everybody say, and now let me a little bit zoom in. Okay, so everybody please read this problem. This is a big problem and pretty interesting problem, actual transformer problem. A single phase 60 Hz generator is supplying power to a load of 3 plus J5 ohm through a short power line with an impedance of that as shown in figure 4.98. Oh, again, I have taken this on from the book. This is very important problem. As I told you that soon I will be assigning you the another set of homework. So you need to understand this problem very clearly. There is good example so in that book. So this figure 9. The voltage as the generator bus, that is bus 1 is 27 at an angle of 0. Determine the following. If the generator at bus 1 is equal to current at bus 2, that is I line equal to I load, then find the voltage at the load bus and power losses that take place in the power line. So everybody see the diagram. Left side, this is the generator, single phase. And rightmost side, there is the load. Load value is given. So therefore, clearly you can see, and in between, this is the power line. So clearly you can see this is a series circuit. So it's not difficult yet. You are able to find out. The question is find out what is the V load value. This means that because load impedance is given, if you can find out what's the I load value, then you just multiplied I load with G load. That will give you the V load. And soon we will be doing. But the second part is complicated. Now see the second part. If two ideal transformers T1 and T2 are inserted at the beginning and end of the line. Now in this problem, first part there was no transformer. Now everybody see, I am inserting one transformer here. I am inserting another transformer here. That is the meaning of this one. Then find out the voltage at the load bus and the power losses in the line. Now see the difference between the two problems. Everything is the same. Generator voltage rating same, line quantity is the same, load quantity is the same. But only problem that is occurring here, you are introducing two transformer. So now in this case, as I told you, if you can, because this is clearly the series circuit, so easily you can find out what is the I load. I mean, you just add this impedance with that impedance. This is your total impedance and your voltage is given. You divide the impedance. So you will be getting current. And because this is series, so it is the same current. Current IG that is the same current IL, the same current IL. So this is easy to solve. And we have done similar problem in the circuit analysis course, simple AC circuit. But
Where
sorry?
where would you be like measuring that voltage from? Like where, if you had a voltmeter on there, where would it be going?
Oh, so we are assuming that on the load side, at the other end of the load, it is connected to neutral. So therefore that neutral point is not shown. So therefore, for example, this point and this point. And you see, because this is load, so definitely for the safety purpose, load is connected with the neutral. I mean, those grounding neutral connections are not shown, but your question, I'm answering to your question. If you have a voltmeter, one point will be here and then other end will be here.
What about for VG?
VG, VG again, you see, this is the power plant, single phase generator. It is producing voltage. This is the voltage. So therefore, one point will be here, other point will be here, then at the neutral point. Definitely
Okay.
there is the neutral. Got it? Yeah.
Yeah, but that's what I figured, but I'm kind of confused why we add the impedances and then um, just like
No, no, you see, because this is the single phase circuit. For example, there is neutral here. Load is connected to the neutral. Then neutral to neutral, there is full connection. Got it? So on the leftmost side, you assume that there is a neutral line which is grounded. On the rightmost side, there is a neutral. So therefore, that neutral is connected to the neutral. So that then it makes the series circuit.
Okay, that makes sense.
Got it? Yeah, yeah. So as I am telling that portion is not shown here. This is called the single line diagram. Oh, can you see the title, figure caption, on-line diagram? I mean, instead of showing all the connection, sometimes it is represented in all line. You see, uh, uh, or even, for example, sometimes it will be the three-phase line, but we will represent it by using only one line. Those things are called the one-line diagram. I mean, in this problem, it is clearly the single phase, but even for three-phase system, sometimes only one line is used. You have to assume that there is B phase and C phase. That is the meaning. Anyhow, so everybody assume that there is neutral. So this is series circuit. How about number two? So now there is transformer. I mean, of course, it looks like it is like connected in series, but is there any direct connection? Because coils are completely separated. So the question is, how would you know the current value here? If you can know the current value here, then you can multiply with the impedance and you will be getting the voltage. And how would you find the total current here? Like in this case, as I told you, because you will be summing up this load and then this load, this impedance and this impedance. That is your total impedance. In this case, what would you do? Would you just add this on and this on? Can you add this plus this? Everybody, could you follow me what I am telling? So therefore, because there is transformer in between, you can directly connect, you can directly sum up this on with this on, because in between there is transformer. So this means that what you have to do, you have a impedance here. You know there is a transformer here. You transfer this impedance at this side. You mean apply this theory. You have a impedance here. You had an impedance. You transfer it on the primary side. Apply this equation. Do you understand, everybody, what I am telling? So therefore, you have a load here. It has 3 plus J5. What is the value of this one if you assume this is in this side? So you see, this is a transformer. Transformer has turn ratio, turn. I mean, soon I am showing you the solution. You will be getting fun. So you have to transfer this impedance here. Then you can connect it in series. But then again, you have another transformer. You have to transfer that impedance here with the help of the turn ratio of this transformer. Only then you can calculate what was the total current. But then again, that is not done. You are able to find out current here. What is the current here? You can't say that the same current is flowing. This is not this circuit. Do you see? So there is again transformer. So again, you have to use this relationship and you have to transfer the current. What is the current here? And then once you get the current here, same current is flowing here. But then again, this current will be different because there is transformer. Therefore, once there is transformer, that creates complexity. That we will be doing so. Therefore, everybody first look this one, first part. So look the diagram. Your question is just to find out the voltage at the load bus and the power losses that take place in the power line. So power losses means in this case, you see there is R and there is L. You will be just finding out I square L just for the resistance part. So in this case, power loss means power loss due to resistance. That is the meaning. So if you can know what is the value of current, then I square R. What is the R value? This 0.2. You just need to know the IL. Now see the solution in the next page. Everybody see what I am doing. I line Vg over this one, G line plus G lot. So therefore in the problem, this was the G lot 3 plus J5 and this is the G line. So without calculator you can sum. So 3.2 and then the J part is 5.6. So that's why this one 3.2 plus J 5.6 and this Vg was given. This Vg value was 277 angle 0 degree volt. That is your Vg. So the result is expressed in polar form. Now, since I line equal to I load, you see, as I told that the same current is flowing. There is no transformer here, so there is no problem. Simply it is the AC circuit. So this current is this current. So the voltage at the load bus, V load, I load multiplied by G load. So your G load is that value, 3 plus J5, and you got the current, just multiply. So I got the I line or I load current, I am just multiplying. This is my result. And then the line loss, that is the copper loss. Everybody see that I told you, P line loss, I square R line. What is the I? Magnitude part. This is the magnitude, this amount multiplied by 0.2. So that 0.2 is this one, resistance value of the line. So you are done. Now I think everybody is fine this part. Now we will go the second part, taking into account the transformer in line. So therefore everybody see. So therefore look this problem first. So the first step we have to start from the right side and then we will go until the generator. So therefore everybody see first what I will be doing, just concentrate this part. I have a load, I have a transformer. I want to transfer this load impedance referred to the primary side. This means I will calculate what would be the value of this load if I transfer it here. So I will be using the turn ratio. Everybody remember 10, 1. This means primary side 10, secondary side 1. So now see, everybody see the solutions of the first part. GL load prime A square G load that we learned. This means N1 over N2 square. For that transformer, it is 10 over 1. So for this transformer, is 10, 1, it is given. So that's why 10 over 1 is squared, 3 plus J5. It gave me 300 plus J500. Now you see that new amount is available here at this point. Now that is in series with this one. There is no problem with that one. That new value, new G load value is in series with this one. Then add with this one. You see that the resulting equivalent impedance, G equivalent, G line plus G load. We got this one. And then again, now this new value, G equivalent value, that is available at this point. Everybody follow, that is available here. Then still you have to transfer because there is another transformer. Now you have to transfer here. Only then you can find out the total current. Your voltage is given 277.0, but you don't know what is the total J. That we are trying to calculate. So therefore, once you get the G equivalent up to this point, transfer that new G equivalent with respect to the primary. So for this transformer, primary side is 1, secondary side is 10. So therefore, everybody see, again, look this up. 1 over 10 squared multiplied by that new impedance. So finally, I got 3.002 plus this. Now I am able to find out the generator current, which is Vg over this new value. So Vg over this new value. So everybody, could you follow me this part?
Yes.
Yes. I mean, everybody, little bit, please be, I mean, very attentive this one. Just the new thing is this one. So, and then once again, keep in mind, I am starting from here. So this means that I have to first transfer this on here. Then I am able to add this on. Again, there is the issue in between. There is the problem. It is hindering me to directly find the current. Again, you have to transfer this on here. That is the thing. The first one is straightforward summed up because there is no transformer. Once there is transformer, you have to transfer it. That's the thing that we are learning today. Okay, so very good. So you understood. And then now everybody look, what is your goal? Your final goal is you have to calculate the voltage here. That was the question. I mean, question is the same for this part and this part. Only difference is the transformer. So this means you have to find out the I load value. Once you are able to get the I load value, then simply multiply it with this impedance. That is your answer. But the question is, right now the current value that we got, Ig this one, is this Ig the same here? Is that Ig value will be the same here? The answer is no, because that is not fully in series. In between there is transformer. So what you have to do, again you have to convert with the help of the turn ratio. This means simply apply the current and turn ratio relationship. So first find out what is the current here. So that's why remember what is the turn ratio? 1 over 10. So therefore, look the last calculation. Here I am finding I line in 1 over n multiplied by Ig. What was my Ig value? This value. And then I got the I line value, this one. So now I got the current here. Then in this portion, that is the same current, no problem. But again, there is transformer. Again, transfer with the help of turn ratio and get the power I load. So therefore, see the another file, another portion. Yes. Look this one. What is I load? N2 over N1 I load. With the help of the turn ratio, finally I got this number. Now I am able to calculate the voltage at the load bus, which is I load multiplied by the G load. Finally, I got this number. And then what is the line losses? Line loss, same as before. I line is square R line. So this I is not this I. This I is that where we calculated I line. This on I line, this value. So 4.7455 is squared. So you look 4.7 squared multiplied by this one. Then I got this watt. So in this case, you see the loss value is fairly low, 4.5039. But everybody see in this case, what was the line loss value? This one. It was quite high because there was no transformer. In this case, transformer helped to reduce the losses. So here I am just calculating percentage of reduction in the line loss. What was the loss before connecting transformer? What is the new loss? Taken percentage with the original loss. So 98.78% loss has been reduced. Anyway, so everybody, could you follow this one?
I had a question. It has like a step up transformer and then a step down transformer. Why do we only do the step up transformer?
Oh, so this is just one example of the problem. For example, this is generator, this is load, and then you see first is stepped up. You see the first is stepped up here.
Yeah.
And then here it is the line, and then again it is stepped down because we are assuming here is the customers or the load.
Yeah. But it looks like we like calculated the current change for the step up transformer. But
No. You remember, here is the turn ratio 110, but here it is 10 on. So
Yeah.
now first look this person. First remember what is the current and the turn ratio relationship. Let me go back. Okay. Look the very last line, this one and this one.
Mm-hmm.
IP over IS equal to NS over NP. Keep in mind. Okay. So keeping that in mind, now for example, look this one, the last calculation. I line and IJ, I line and IJ. So this means here it is I line, you have the IJ. So, and then N on is 1, N2 is 10. So therefore assume that your I line is I2 and IJ is your I1.
Yeah.
So therefore see the how it is calculated. Yes, look. So I line over IJ. This means I2 over I1. I line
So
is your I2.
in
Equal.
this case, IG does equal I load because it goes into like.
No. IJ is this generator current, main current. You see?
Yeah.
This is the IJ and I line
Yeah.
is for this person and I load is here after this transformer.
Yeah.
So
But does it not end up?
Sorry?
Does it not end up being the same because it goes into a step up and then a step down with the same
Yeah,
ratio, or like it?
Exactly. So therefore, once you get this current throughout this portion, this is the same, but you can, the same current will not flow here because there is a transformer. It will be related
Yeah.
with the turn ratio. That is the thing. In the top portion, A portion, once I calculated IG, I use the same value all the way. But in this case, everybody see, in this case, because there is transformer, I calculated IG, but I can't say that is the same value because there is transformer. So it is related to the turn ratio that we are doing. Then once I get the I line, so all the way it is the same, I mean, until the primary, and then again there is transformer. So I load will be different than the I line. Got it?
Mm-hmm.
Yes. So therefore, here you see the last part. We are using that relationship. You assume this is I2, IG was on the left side, this is ion. So I2 over ion is N1 over N2. Accordingly, this 1 over 10 is the turn ratio value. And then in the next part, here you see, I line and I load. Actually, this should be, I think, the I load and this is the I line, yes. So, and then although in both cases it is written like I load, because you see this one, this portion is all the way the I line, but this is the I load. So twice like the same thing has been written. Actually, one will be load, other will be the line. So this means if you say this is I2, then this I line will be the I1. For this transformer, you have to assume that this is I1, this is I2, and 10 is the N1 and 1 is the N2. Got it? Jared, is this fine?
Yeah.
Yes.
Mm-hmm.
Yeah. And then to calculate the power loss value, you use this current, I line current, because which you calculated first. But in the previous problem, I mean, it is the same. All three current were the same. That's the thing. So therefore, I mean, everybody keep in mind, I mean, this means once there is a transformer, of course, currents voltage are related with the help of the turn ratio, but the impedance is related to that equation. I mean, A square into GL. That is the thing.
Can you go back to where you got IG? Because I did something wrong. I got like,
IG?
yeah.
Okay, so look here, IGI line. So you remember this one?
Just the math for it. I did
Oh,
the,
okay. Okay,
I think
okay.
I did like some number thing wrong or something.
IG value. This one. You got the different number? So
Yeah, I know what I did wrong. I didn't square the turn ratio. I just divided it by 10. So
Oh, okay, okay. You look at from the beginning, like a square. Yeah, yeah. So therefore,
yeah.
yes, from the beginning, like there is on squared here, and then again there is squared here. Yeah.
Yeah. I did from load to line right, but I didn't do from line to source right. So thank
Okay.
you.
Okay, I got it. Yeah. So first here we are converting that load into an equivalent, then we are adding with the line, and then we are converting using this equation. So this is now my total impedance, total equivalent impedance. That is being divided. I'm dividing the voltage by that value. Yeah. So this is the actual current or the total current Ij. So is everybody fine?
Yes, yes, so far.
Yeah, yeah, yeah. So please once again after the class you all look, so then you will be getting it. Yeah. And then everybody, you must understand so these things, then you will be able to solve the homework problem, second set of the problem. So therefore look this problem. So once again, and then this one, and that was the simple one, and then this one. And then again in next class, I will be discussing other type of problem, like calculation of efficiency of transformer. And before that, there are two standard tests. It is called the short circuit test and open circuit test. We want to, today we discussed mainly the ideal transformer, but next class we will be discussing the real transformer. We want to show that there is some resistance both in the primary side and secondary side. So if we include the resistance, then there will be some loss. And we want to find out the equivalent circuit parameters. And that is, you'll be like your lab number 2, experiment number 2 in the lab about transformer. So that thing I will be discussing, followed by example, numerical example. Those will be a little bit different. And after that, I think you are able to solve most of the homework problems. So probably I will be uploading the homework too by Sunday, but then you have to wait until the next class, until Tuesday, to solve most of the problems, homework problem. Okay, so therefore, I think that's all today. Is there any questions, comments from anybody? Is everybody fine so far?
I think so. Thank you.
Okay.